The intent here is to give you an overview of what we're talking about when we talk about biofilm models. The consensus, at least in engineering, is always that we're using 1D models. And there's a mass balancing that forms the basis of all that. And although we may disagree on some points, this fundamental structure of the 1D model and mass balancing on a 1D model structure, on that there is 100% consensus. So we'll take a look at that. We'll discuss a little bit about how this idea of mass transfer boundary layer thickness is implemented in code, as well as attachment and detachment from biofilms, handling how we handle multiple biofilm layers, and then a little discussion around biofilm density. I think it was Harold who brought that up as a point. So we'll show what that means when we're actually looking in code. Anything to add there, Martha, or should we just launch into it?
Doing great, Dwight.
Good stuff.
That's good.
Okay, so the fundamental basis of all of this 1D biofilm model. Thank you, Kelly, for taking on that point that that a basic biofilm model is really just one layer, which we can see up here, a biofilm layer, and then a bulk liquid layer, and that's sort of the irreducible complexity of a biofilm model. We only need one layer. We have bulk liquid, and then what we do is we perform mass balances. So in mathematical terms, the derivative with respect to time of the mass in the biofilm, and the derivative with respect to time of mass in the bulk liquid. And this is really simple. I think we've all learned this in school. Mass balance is just what goes in minus what comes out plus reaction terms. So that's what we're going to be looking at. So, I mean, what comes in and what comes out, we could be talking about bulk liquid flow. We could be talking about diffusion in and out between bulk liquid and biofilm. We could be talking about attachment, detachment. If you can think of other processes, I'd like to hear them. And then reaction, when we implement this in code, ultimately it comes back to activated sludge models. That's what we use. So we use biological models that were fundamentally developed for suspended growth processes. So that's how we model the reaction term, which is interesting. And then, if you go back to your theory from university, if we solve for this where the accumulation term or DDT is 0, then of course we have steady state. Okay, so what we have here is we have a little Excel file which shows how this is implemented in Sumo using the simulation programming language that Sumo uses called Sumo slang. So what this shows here is basically that same mass balance equation where we have the change in mass with respect to time, and it's equal to what comes in minus what goes out plus the reaction term. And so if you look for expression 1 here represents the bulk liquid. So that's the first compartment in the biofilm model. And it's equal to what comes in minus what goes out, so effluent, plus diffusion. And diffusion can be positive or negative. So what's transferring across between the bulk liquid and the biofilm, and then plus the reaction rate. And so there's the mass balance equation implemented in the simulation package, where each element or each term, if you will, in the biofilm mass balance is a line item in a matrix. So influent, effluent, diffusion, and biological reaction. Similarly, if we look for the biofilm itself, it's almost the same, except we don't have inflow or outflow because the liquid flow is always communicating with the bulk liquid, not directly with the biofilm. So actually that was the mass balance. I failed to point it out for soluble material. If we look at for particulate material, then the mass balance is similar. So the change in mass with respect to time is equal to in minus out plus the reaction. But now the individual terms that impact in and out are a little different. So again, if we look for the bulk liquid, That's represented by the first compartment. So layer 1, if you will, or compartment number 1 is equal to what comes in minus what goes out. But now we're no longer talking about diffusion, because we don't have soluble components, but we have particulate components. And so we're talking about attachment, detachment, even we might be talking about internal solids transfer. A lot of these models work with internal solids transfer of solids between internal layers. And then, of course, the biological reaction inside, well, in this case, it would be the bulk liquid. If we jump to the second column, expression number 2, now we're representing the biofilm compartment. And now the biological reaction represented here would represent the biological reaction in our biofilm. So that is, I mean, that's it. And I would hazard to say that you know, if you look across all the simulators that are being used today in industry, in engineering practice by consultants, they all have this fundamental form. There's no difference. There's complete consensus around this structure for an engineering biofilm model. They're all 1D flux models. Where we do get some differences, you know, might be in how, you know, if you look, for example, here, diffusion, you know, what does this actually represent? I mean, you can see this dm comma diff comma sv square brackets 1. What does that actually represent? And the different elements in the mass balance can be thought of as submodels. So there's a submodel for diffusion. There's a submodel for the biological reaction rate. You know, that could be ASM1, that could be ASM2, that could be whatever the case might be. And it's here where there are differences in approaches between different software vendors and between different practitioners. So we'll dive into that a little bit. So answer the question, okay, great. Diffusion we see in the mass balance, it's dm comma diff comma sv square brackets 1. What is that supposed to represent? So the fun thing with Sumo as a simulator, which I really like, is that the model itself is open source. And so if you want to find out what one line item in a mass balance represents, I mean, the code is open source, so you can go and see, oh, dm comma diff comma so-and-so is equal to minus f comma diff comma tc comma l, whatever that means. And then if you say, well, what is that actually equal to? That doesn't really help me. But you can back out of the code and say, well, okay, I'll do a control search inside Excel, and I'm going to find out what this f comma diff comma etc. represents. And you can back into basically the fundamental equation or relationship that underpins, in this case, the diffusion model. And so here you can see some parameters that start to look a little bit familiar. So we've got this capital DF, we've got this capital AF, maybe this capital D stands for a diffusion constant, maybe this capital A stands for an area of the biofilm. You can see 2 numbers being subtracted, and then you can see we're dividing by ZBL, where BL, you know, suspiciously, maybe that stands for boundary layer. And so you can back into the code and always fundamentally back into what the fundamental parameters and definitions are for all the aspects of the model. So in this case, what we see here is simply the diffusion rate ultimately is being calculated as fixed diffusion constant, that's the D, times the area of the film, there it is, and then times a gradient of substrate between the bulk liquid and what's inside the biofilm. And then finally, we're dividing by a boundary layer thickness. So very, very familiar equation. And actually, I would also hazard to say that there's no controversy on how this is being implemented in simulators either. Diffusion is always being represented using this fundamental equation. And if you care to look it up or challenge that, I mean, just look it up on Wikipedia. You know, everybody knows if it's on Wikipedia, it must be right. So I looked up fixed diffusion law on Wikipedia and came across this bit of text where you can see the same relationship. So J, where J represents the flux, and then D is our diffusion constant, and then, you know, there's your gradient, and there's your boundary layer thickness. Okay, so there it is. What do we conclude from this? You know, we look at this equation. Well, if we're dividing by a boundary layer thickness, that means if boundary layer thickness is a smaller number, because it's in the denominator, when you divide by a smaller number, you get a bigger number over here. So thin boundary layers make for fast diffusion. My experience working full scale is that boundary layer thickness ends up being a bit of a lumped parameter, not just for the actual liquid layer thickness on the biofilm, but also for mixing in the tank. And this is particularly true in my experience with fixed media, where you have a cassette of tightly packed hollow fibers, and then you have to try and get flow from outside the tank, outside the cassettes, and get it to come inside the bundles of fibers and come into contact with that liquid layer thickness. So yeah, just another thought there, that we, in some situations, we might be dealing with this parameter as in fact a so-called lumped parameter, which then has to take into account other inconvenient things that occur at full scale. Great. And there's a comment that I don't want to get into. So schematically, yeah, there's where we would find our so-called boundary layer thickness. In case anyone was confused by that, that's kind of what we're talking about. So how does it work then when we're calibrating these models? Well, you know, ultimately, what we're interested in is treatment efficiency or fluxes. And what contributes to that is media surface area, substrate gradients, but then boundary layer thickness. Here we have it. And what impacts boundary layer thickness? Well, probably more than one factor, which is kind of what I was getting into. So that's just represented here kind of visually, that, you know, we should be thinking maybe a bit about media geometry, whether we have cassettes, what the packing density is, what the tank mixing is. So all things to sort of keep in mind. So a question we might ask is, you know, in parts 3 and parts 4 of this workshop, if you think about, you know, highly mixed or poorly mixed tanks, how might you account for this in the model? You might account for this through changing your boundary layer thickness, but it depends. So that's our statement that we're going to say a lot when it comes to biofilm modeling, is that it does depend. Okay, so diffusion layer thickness and fixed diffusion is supposed to be fairly non-controversial, a high degree of consensus more or less around at least how to structure a model of that. Let's dig in a little deeper and talk about attachment. So again, here's our mass balance. We're mass balancing in our model particles, and we have this line item that's called attachment from the bulk phase. So then, you know, how do we define that term? F for flux, I guess, ATT for attachment, and then SV probably stands for the state variables. So let's dig into that a little bit. So, you know, here you can see in the Sumo code, if you go in the underlying Excel file that codes that model, you can find the attachment rate, and you can see how that's defined. And it's defined in terms of this other term here, F attachment XTSS, which is then defined in the line below it. And then we can find the fundamental equation in which we have the attachment rate is equal to some parameter called R attach. times the area of the film times the concentration of TSS in compartment number 1, which represents our bulk liquid. So there we are able to dig down to the sort of lowest level or granular level of the attachment model in the biofilm. And we should think of this as a sub-model. So it's part of the overall 1D model, but you know, there's no reason in particular why it necessarily has to be this way, unless you really think that the attachment of particles onto a biofilm are first order with respect to the concentration of MLSS in the bulk liquid. Yeah, the consequences of this, okay, so we have a first order attachment rate with respect to bulk TSS. What's this mean? It means that attachment increases with MLSS. It also means that all particulates attach at the same relative rate. So it does not assume that some of your particles in the mixed liquor, or maybe coming from the influent, are stickier than others. Although you could change that. It is an open source model that we're working with, so you could make that change if you were so inclined. Okay, I'll move on to detachment, Leon, because that was a great segue that you gave me, actually. Okay, so we talked about attachment. Let's talk about the detachment. So here again, in our mass balance, it's a line item, but how we're going to define this parameter here, you can consider that a sub-model. So it's a sub-model, and you could define that model more than one different way. So let's take a look at how this is defined in the Sumo model. So here we see, I mean, it's defined here. You can find it here on the symbol here is defined according to this expression here. So this is sort of not very informative, but if we back into how this F comma DET comma XTSS is calculated, then we can find fundamentally the underlying equation. And so what we have here is we have F dPm, whatever that is, not really sure. And then we have this R detach, which sounds like it's the detachment constant, but it has this little comma SL. So that's interesting. Maybe we want to look at that up. And then we have AF, which just stands for the area of the film. And then we have XTSS, so that's the TSS concentration, in compartment number 2. So actually, now it's responding. Detachment is first order with respect to TSS in the biofilm layer. And finally, it's being divided by the boundary layer itself. So there's a bit to unpack here. Some of these parameters we recognize, we know what they are. For example, this one we know what it is, this one we know what it is, this one we know what it is. But what are F dPm and what are R detach comma SL? So we'll go back and you know, we'll try and find out in the code, what is this and what is that guy? So yeah, what are those two guys? Let's find out. So R detach actually is a parameter. So there you can see a hard-coded number there. But notice it's not R detach comma SL. So this is just R detach. But the equation we saw had R detach SL in it. So we need to find out then, you know, what is R detach SL? And we find that it's defined here in terms of R detach, which is our constant. And then here, this, what we'll call basically, that's a what in model speak we call a switching function. So it's just a number that varies between 0 and 1. And you can think of it as a switch. We call it a switching function because it's like a light switch. You can use it to turn things on and off. So R detach SL, if you do the math on this calculation here, you know, if you go into Excel and you plug in this formula, you'll find that If you are below your target biofilm TSS concentration, then our detach SL is 0% of the actual number you put in. So there's no detachment when you're below your target solids concentration in the biofilm. But as you approach that target solids concentration in the biofilm, you can see detach is eventually turning up to 1, or another way of seeing it is 100% of what the underlying fundamental parameter is. And so we use this switching parameter in this particular model to basically force the model to the biofilm thickness and solids concentration that we want. This submodel that we see right here is appropriate for constant thickness biofilm models. So it's analogous to if you had an activated sludge process where you were trying to maintain a constant inventory of solids here in this zone. Then, if you said, well, I want to operate, let's say, at an MLSS of 3000, then you would adjust the wasting until you achieve that target of 3000 milligrams per liter. So it would be like a switching function that you would apply to Q was to achieve your inventory target here. So in the same way, this is our switch here that allows us to achieve this underlying parameter here, XTSS target. Let me see what's next, because I'm drawing a blank on memory. Aha, Kelly. This is you. So here we go from 2 layers, or 1 biofilm layer to multiple layers. And we as organizers, we kind of asked you to defend that point that the minimum number of layers in a biofilm is 1, but it sounds like practically speaking, everybody's always using multiple layers. And so just from a conceptual point of view, I put this out here to say that if we're thinking in terms of the mass balance, does this make life more complicated? Not really. It's the same framework, this mass balance where we have line items, where we have inflow and outflow only for the bulk liquid, and then this expression 2, if you imagine that this represents the first biofilm layer, and then layer 3 to however many number of layers you have, it's the same equations over and over. It just, you iterate over how many number of biofilm layers you have. And so I think that's something to keep in mind, that the 1D model, it has a lot of flexibility. And from my experience, it's I don't ever change the number of model layers. Okay, I think to maybe provide a segue to the break into part 3, I'll jump to there was some talk about recommended ranges. So maybe I'll just end with this in terms of part 3, when we think about calibrating our models to design curves or full-scale systems, we have to think about some of the model inputs and how we might be changing those. So in the case of a fixed thickness model, here are some ranges that I would suggest maybe are appropriate for different levels of BOD loading. Kim mentioned a different parameter to be thinking about, which is temperature. Thinking about 10 degrees versus 20 degrees Celsius. So that's something else. But yeah, some ranges here, maybe just to be thinking about as we go into the part 3 exercises. With higher BOD loadings, you expect to see higher biofilm thicknesses. And if you have a variable thickness biofilm model, then perfect. Hopefully it's predicting that for you. But if you don't, then you need to manually input that. And the same goes for the specific mass of the biofilm. That is to say, how many grams of dry solids there are per square meter of media. And then mass transfer boundary layer thickness also can be variable.